Hello all, welcome to the next lecture of electromagnetic theory and transmission line. So in the past lecture, we have discussed about the types of transmission lines and the primary constants of a transmission line. So today in this lecture, we will be continuing our discussion with the general solution of a transmission line. So let us here in what we mean by general solution means we are deriving the expressions for voltage and current in case of a transmission line at any point x. Okay, yeah. So for this, let us consider a transmission line. So I have a source point and I have a receiver point. So this is my transmission line. So on this transmission line, let us consider a point P dash and another point QQ dash. So let us consider a small portion of this transmission line. So the small portion of this transmission line is between the points PP dash and QQ dash. Now we know that this this portion of the transmission line has or exhibits the properties of resistance, inductance, capacitance, and conductance. So all of that put together, we can say that this small portion of the transmission line we can approximate to be having a circuit of as below. So you can assume that this has let us consider this has the structure the equivalent circuit to be like this. So this is the inductance, this is the resistance, this is the so let us consider this the length of this particular line to be dx. Okay, so I'm considering of it is of a very small distance, very small length. So let us consider it as dx. So this is rx, this is cx, and this is gx. Okay, so if R is the primary constant of the transmission line, so then we said, right, the value of Rx will be equal to small capital R into dx, and similarly the value of Lx will be equal to L into dx. Okay, and Cx will be equal to C into dx. Okay, and Gx will be equal to capital G into dx. So we are considering that RLCG are the primary constants of this transmission line. So we said that we have to know that this primary constant RLCG, right? Whenever we say primary means they are defined with respect to unit distance. Okay. So this as they are okay. So this values of the transmission line we can obtain like this. Now let us assume that the voltage at the point P be capital V, right, and the current at the capital P will let us assume it as I. Okay, so V is the voltage at the point P dash, and I is the current at the point P dash. Okay, so because there is a small change, right? There is a small distance between P and P dash. Let us assume that at Q the voltage changes to by a value called as dV. So the voltage at the point Q is V plus dV, and the current at the point Q is I plus di. There is a small incremental change where dV represents incremental change in voltage and di represents incremental change in current. So there is a small incremental change in voltage and small incremental change in current from the point P to point Q. Okay, so this is the setup that we have. Okay, so we have assumed a transmission line, right? Let us consider that the transmission line has the primary constants RLCG, right? We have considered a small portion of the transmission line between the points PP dash and QQ dash. Okay, so between these 2 points we can represent the transmission line as in terms of the primary constants or in terms of the circuit elements like this. Okay, so this is the circuit approximation of the transmission line for this portion. Okay, so for this portion, right. Now, so these values, what are the values of Lx, Rx, Cx, Gx? So these are the values. So this is the primary constant multiplied by the length of the portion. So length of the small portion, which is dx. So we got something like this. Okay. And again, I'm assuming that the voltage at the at the point P is V, and the current at the point P is I. Similarly, at Q, I'm assuming that the voltage has changed by a small value. So the dV, right, and current is changed by a small value I plus di. Okay, so here the change can be positive or negative, right? dV and di represents both. Okay, right. Now, now, what is the difference between? Let us take the differences between the voltage and the current. Okay, so yeah, so the voltage at the point QQ, the difference between the voltage at the point QQ dash, we can write that difference as V minus V plus dV is equal to, in terms of, so V is equal to I into R using this formula. So generally V is equal to I into R. So using that formula, so the voltage at the QQ dash, the difference, right, the difference between the voltage difference between the 2 points, I'm assuming. So this can be written as, in terms of current, we can express that as I. What is I here? So here I is I here, right? Yeah, so this can be written as V minus V plus dV is equal to, or oh, sorry, so we, yeah, that's what we write. V plus dV minus V is equal to R plus j omega L, that is the impedance that we have in the series arm, into, right? So because this is Rx and this is Lx, right? So we need dx. So the into these two quantities should be multiplied with the element x, okay, into the current that is there, okay. So this is the expression for right change in voltage. Similarly, for change in current, I get I plus di minus I is equal to, right here, when I am writing expression for current, current is nothing but I is equal to V by R. So V by R, but we can also write 1 by R as, right, 1 by V by Z. That's what we write. I is equal to V by Z. Okay, or this can also be written as I is equal to Y into V. Okay, so Y here represents admittance. Okay, and the admittance is nothing but this part, this parallel portion admittance. So we can write that as G plus j omega C into dx for the small length into V. So by using the general expressions, V is equal to IR and I is equal to G into V or Y into V, we have written the two expressions. Okay. So this is what the two expressions are. So from this, right, so VV gets cancelled. From the first equation, I get dV is equal to R plus j omega L into dx into I, or we can also write this as dV by dx is equal to R plus j omega L into I. Okay, so let this be equation 1. Okay. Similarly, from the current equation, di is equal to G plus j omega C into dx into V. Okay. So di by dx is equal to G plus j omega C into V. Okay. So let this be equation 2. So we got two equations for voltages and current. Okay. So two equations for voltages and current. So one is dV by dx is equal to R plus j omega L into I, and another is di by dx is equal to G plus j omega C into V. So from this we can get the expressions. Yeah. So I think till this point it is very clear. So what we have assumed is, we have assumed a transmission line. Out of that we considered one small portion between the 2 points PP dash and QQ dash, and using the general formulas of voltage and current expressions, I have written V is equal to I into R. So R or Z into I. Here the Z is R plus j omega L, right? And I is equal to Y into V. So Y here is admittance, here is G plus j omega C. So using these expressions, I got the two formulas for dV by dx and di by dx. Okay. Yeah. So let us continue from this. Yeah. So let us take this equation 1. So let us differentiate this equation 1. Differentiate the equation 1, right, with respect to x again. Okay, with respect to x again. So this will become d square v by dx square is equal to, so r plus j omega l is a constant with respect to x. So we write as it is r plus, because these are primary constants, right? So we don't have anything related to them. So r plus j omega l is constant. So we get di by dx. Okay. So we have taken the equation 1 and let us differentiate the equation 1 with respect to x. So d square v by dx square is equal to r plus j omega l into di by dx. Okay. Right. Now from the equation 2 we have the expression for di by dx, which is nothing but this. So therefore what we can write is d square v by dx square is equal to r plus j omega l into g plus j omega c into v. That's what di by dx is. Okay, so I'll get something like this. Yeah, right. Now this is equal to d square v by dx square is equal to, right, let us assume that this constant, whatever the constant we have, r plus j omega l into g plus j omega c, let us assume that this value is equal to gamma square, where gamma is a constant. What is this constant? We will discuss in the next video, right? So let us assume, as of now, let us assume that this value r plus j omega l into g plus j omega c is equal to some constant gamma square. Okay, so therefore this will become d square v by dx square is equal to gamma square v. Okay, or I can also write this as d square v by dx square minus gamma square v is equal to 0. Okay, so this is the expression for voltage. Okay, yeah. So simple, I've got equation 1 and equation 2. From that I have differentiated the equation 1. Okay. So with respect to x, so we got d square v by dx square is equal to r plus j omega l into di by dx. So from that I have substituted the value of di by dx, which is g plus j omega c into v square. We are assuming this term as a constant, which is nothing but gamma square. So that is what I got. Similarly, in the same way, if I take the equation 2, yeah, let us call this as equation 3 and let us put this aside. Similarly, let us take the equation 2, okay, and do the same analysis. So, okay, that is di by dx is equal to, the equation 2 is di by dx is equal to g plus j omega c into v. So, again, differentiating this with respect to x, let us differentiate this with respect to x. So, we get d square I by dx square is equal to g plus j omega c into dv by dx. Okay. Right. So from equation 1 we have the value of dv by dx, which is nothing but r plus j omega l into, right, I. Okay. So again, letting this r plus j omega l into g plus j omega c as a constant that we assumed as gamma square. So I get d square I by dx square is equal to gamma square into I, or, right, what I get is d square I by dx square minus gamma square I is equal to 0. Okay. Yeah. So this is the expression or the differential equation we get for the current. Okay. So for voltage, we get a second order differential equation like this. So d square v by dx square is minus gamma square v is equal to 0. And the expression for current is d square I by dx square minus gamma square I is equal to 0. Okay. So, right, these are the expressions for voltages and current at the point, at any point x. Okay. Yeah. Now, if I look at these two expressions, both of them are second order differential equations. Okay. So if I consider this equation d square v by dx square, d square v by dx square minus gamma square v is equal to 0. So this is a second order differential equation for voltage. Okay. So the variable here is x. Okay. So gamma square is a constant, right? So it's x. So if I solve this for this equation, I will get the or solution for the voltage. Okay. So the general form of solution is generally given by V of x is equal to, now V as a voltage variable of x, or just we can also write capital V itself, V or V of x is equal to, so what is the general solution? We need one constant. So let us assume that as V plus into e power minus gamma x plus V minus into e power gamma x. This is the general solution, right? Okay. Yeah. So V of x is equal to V plus into e power minus gamma x plus V minus into e power gamma x. Okay. Similarly, right, if I take this as the current expression and if I write the general solution for that, so I'll get I of x is equal to I plus into e power minus gamma x plus I minus into e power gamma x. Okay. Yeah. So, correct. So these are my two important expressions. So these are the solutions for voltage and current of a transmission line at any point x. Okay. So if I know the x is nothing but the distance. So right here the distance is taken from the source end. X is the distance from the source end. Okay. So if the value of x is known, right, then we will be able to calculate voltage or current at any point x using these expressions. Okay, so here V plus and V minus, similarly I plus and I minus are constants. Okay, so in some textbooks or in some cases we can also assume them as ABCD values. Okay, you can take them anything, right? These are basically the magnitudes, right? Constants or magnitudes. Okay, constants of the solution, or we can also consider them as the magnitude part of the solution. Okay, so right, right. That is the thing, and you can see that this is a exponential term. One is having right a positive phase constant, and another is having negative phase constant. Okay, one is right. One expression represents this way, and one expression represents this way. Okay, so right now. These are the voltages or currents at any point. Okay. The point we have to observe here is, so these values V of x and I of x are not defined at a particular time instant. Instead, these are the average values of the voltage and current at a point, or you can assume it as the total sum of all the voltage and currents at a point at all time instants. Okay, so understood, right? So if I consider any point x, let us say this is the point x. Now V of x here represents the voltage at the point x, okay, as a sum of all the points, all the voltages, okay, or the voltages at different time instants at that particular x. Okay, because see, whenever I am applying an AC signal, the value of voltage, right, will not be same at all point, at all time instants, isn't it? So it is varying. Okay, it is varying or it is changing with time. Okay, so here V of x represents the sum of all the voltages, okay, or average value of all the voltages that are appearing at this point, right, at this point at all time instants. Okay, so if I want to know, or if I want to know what is the voltage at a particular time instant, okay, that's what we call it as instantaneous voltage. Okay, so if I want to know, right, if we want to know what is the voltage at a particular time instance, then we can, right, then we have to multiply these terms with respect to the instantaneous quantity, which is called, which is generally given by e power j omega t. Okay, so I write that as Vi of x is equal to, that is instantaneous voltage, okay, at x and t. Okay, so instantaneous voltage at x is given by V plus into e power minus gamma x plus V minus into e power gamma x, right, into e power j omega t. Okay, so when I multiply this voltage with respect to this, I will get something like that. So this is equal to V plus into e power. So if I multiply these two, we can write that as e power j omega t minus gamma x. Okay, and V minus into e power, right, this will be now, we can write it as e power j omega t plus gamma x. Okay, so these are the two things that we get. Okay, So one will be e power j omega t minus gamma x, and another will be e power j omega t plus gamma x. Okay. So yeah. So in general, gamma is also a complex quantity. Okay, gamma is also a complex quantity. So if you would have studied about the networks theory, we can write this gamma as alpha plus j beta, which we will see later. So right, gamma is also a complex quantity. So therefore, this complex, this exponential can be split into two parts. So if I write gamma is equal to alpha plus j beta, so what I can do is v plus into e power j omega t, right, minus, so this can be written as alpha plus j beta into x. Okay, and similarly v minus into e power j omega t plus alpha plus j beta into x. Okay, so from this we can write, okay, just expanding these terms. So Vi of x, the instantaneous voltage of at any time instant, Vi of x is equal to V plus into. So what I am doing is I am taking the real part, right? This is a complex terms. So let us write the real part separate and imaginary part separate. So real part will be only alpha x is the real part. So e power minus alpha x is the real part of this, and complex terms. So if I take j common, omega t minus beta x will be the complex term. Okay, from this. Similarly, this will become v minus into e power alpha x into e power j omega t plus beta x. Okay, right. So yes, so we will get the solution for voltage, instantaneous voltage, that is the voltage at any time instant, like this. So V plus into e power minus alpha x into e power j omega t minus beta x plus V minus into e power alpha x into e power j omega t, right, minus beta plus beta x. Okay, yeah. So right now, if you observe or if you look at this two expressions, right? So you can see here, this is e power j theta. Okay, so theta is equal to omega t minus beta x, which represents, generally we write e power j theta as cos theta plus j sin theta. Correct? Okay, so this is cos theta plus j sin theta. So therefore, I can write this as cos of omega t minus beta x plus j sin omega t minus beta x. Okay, so this is the term that we get for this expression, right? Okay, similarly for this expression, that is where e power j omega t plus beta x, so this is also same, only thing is cos omega t plus beta x. Okay, and this will be j sin omega t plus beta x. Okay, yeah. So we can see that, right, the rest of the parts are only magnitudes, right? So v plus into e power minus alpha x, this is just a magnitude, this is just a real quantity, right? So okay, this is a constant quantity, this is also a constant quantity, right? If you observe this part and this part, so this part e power j omega t minus beta x, we can write it as e power j theta, so like this, and e power j omega t plus beta x is like this. So both these are, right, okay, functions of cos and sine. So this will give us a sinusoidal variation, and this is also going to give us a sinusoidal variation. Okay, so this is a sinusoidal wave, and the resultant of this also, okay, also will be a sinusoidal wave, but right, exponential nature. Okay, but the point of interest that we have is, so this, if you look at this, so this is omega t minus beta x, so the phase of this is omega t minus beta x, whereas the phase of this is omega t plus beta x. Okay, that means as the value of x increases, okay, if you look at this, so as the value of x increases, right, as the value of x increases, right, so when the value of x increases, the phase of this term, the phase of this wave, right, the phase of this wave, okay, cos omega t minus beta x, right, so as x increases, the cos theta value, you could see the theta value of this is going to get reduced because omega is fixed, time instant, you are talking about at one particular time instant. Beta is the phase constant, which we'll discuss later. That is also a constant. So as I vary the value of x, right, what I can observe is the theta value here, okay, the cos angle is going to be, right, getting reduced. Okay, so whenever x is equal to 0, this will be at the maximum cos omega t, right? So from there on, we can see that as we travel towards right, xl. So this is the length of the transmission line. So and x means, right, I'm increasing x means the length of the wave is increasing. Okay, so as I am moving right towards the load end, right, the value of x increases means this is the source and this is the load. So the length of the the points, right, we are moving towards this. Okay, we are moving from the source to the load. Okay, so whenever this is happening, we can see that the phase angle of the cos is getting, right, shifted, right? Okay, the phase shifting, whatever that is happening, the phase shifting is towards the right side. Okay, so the phase is getting shifted towards the right. Okay, understood? So like this. So at this point, let us say the right, I have a wave like this. Now the point here. So as we move towards, right, as we increase, right, the wave is getting phase shifted, the more and more, right, more and more. So each point is getting traveled, right, towards, right, each point is getting shifted towards right. Okay, shifted towards right. Okay, similarly, right, okay, I hope you have understood. So what I'm saying is, as the value of x is increasing, right, the phase shift, the phase lag, whatever happens, right, this basically represents a phase shift, right, omega t minus, that means the signal shifting. Okay, the signal shifting is, right, tending towards, right, the load end. Okay, it is moving towards the load end. So right, it is getting shifted like this. All the points are traveling along the wave in this direction, in the forward direction. Okay, next, right, coming to the second part, second wave. So if you observe here, the phase shift here is omega t plus beta x. So as the x value increases, this represents t plus a, right? This represents a t plus a. So which indicates a phase lag, okay, or a shift towards the left side. Okay, so that is, right, here the wave, right. So if I consider, okay, if I consider this as my this is my transmission line. Okay, so this is the x value. So as I increase the x value, that is, as I move towards the load end, I can observe that the phase is getting shifted. That means this wave is traveling, right, like this wave is traveling, right, in the opposite direction. So any point, right, any point that we have, right, is moving towards this. Okay, is towards the load end. Okay, sorry, towards the source end. Okay, so here as the x value increases, the shifting, this is t minus a, so which indicates the shifting towards the right side, and t plus a, which indicates the shifting towards the left side. Okay, so these two quantities, right, there are similar quantities, both of them represent sinusoidal variations, but only thing is, one is a wave traveling from the source end to the load end. Okay, so one is a wave that is moving on the transmission line from the source end to the load end, and another is a, right, this is another quantity which is as a wave traveling from load end to the source end. Okay, load end to the source end. So this represents, right, in short we can say that, right, from all these discussions, in short we can say that, right, okay, the voltage, the instantaneous voltage of at any point x on a transmission line, right, is a sum of a forward traveling wave, right, from source to load, and a, right, reverse wave from load to source. Okay, so you have one wave that is traveling from source to load like this. So this is the forward traveling wave from source to load, and another wave, there is a traveling there is another wave that is yeah, there is another wave that is coming from the reverse end, okay, from the load end to the source end, okay. So this is load to source reverse wave, okay. So this component is a backward wave or at reverse component, and this wave is a forward wave, okay, or the forward direction wave, okay. So because of this, we can observe that at any point, right, at any point, the voltage, right, the instantaneous voltage is a sum of these two waves, okay. So therefore, we can say that there will be, right, reflections, and because of that, we will get standing waves, okay. A standing wave pattern is generated inside the waveguide, okay, inside the waveguide. So right, so now, as of now, right, from the general solution, okay, we have concluded that, right, the voltage, the instantaneous voltage of on a transmission line at any point x is basically sum of a forward traveling wave and a reverse traveling wave, okay. So the same is the case with the current also, okay. Current is also same, right. We can do the similar analysis for the current also, right. I can get the same expression, ia of x will be same, I plus into e power minus alpha x into e power j omega t minus beta x, okay, and this will be I minus into e power alpha x into e power j omega t minus beta x. So same expression for current also in the same way, okay. So right, both voltage and currents will have forward and reverse components, right. Therefore there will be reflections on a transmission lines, okay, right, and these reflections or these reflected waves create a standing wave pattern, okay. So that's what we observe from this general solution of the transmission line, okay, right. So I hope you have understood. Just a quick conclusion. So general solution means here we are deriving the expressions for voltage and current. So for that, we have started with considering a small portion of the transmission line between 2 points p dash and q dash. So from that, I have derived the expressions for voltage and current, okay, and then I got a second order differential, the voltage and current are second order differential expressions. So I have solved, I have written the general solution for them, and from that I observed that it has two components, right. Looking closely at those two components, these two represents sinusoidal variations. Both of them are same in nature. Only thing is, one represents a wave traveling from source to load, which is what we call it as a forward wave, and another represents a wave that is traveling from load to source, which represents a reverse wave, okay. So in general, on any transmission line, we have the, at any point we have the overlap of both forward wave and reverse wave, and hence we get a standing wave pattern, okay. So that concludes this topic. So from next, in the next topic, we will be discussing why these reflections occur, right, how can we minimize them, right, and we also discuss what are the different parameters that exist on the transmission line to be considered, okay.